Hello and welcome to lecture number 3 for Introduction to Astronomy AST 1002. Today's lecture topic is on Newtonian gravity. The learning objectives for today's lectures are that we will learn about the astronomers Tycho Brahe and Johannes Kepler and how their observations and analysis of data led to Kepler's three laws of planetary motion. We'll also learn about the famous English physicist and mathematician Isaac Newton, who famously came up with these three laws of motion and some universal laws of gravity. We'll also then learn about how gravity and orbits behave in our solar system and how the combination of Kepler's planetary laws and Newton's laws of gravity helped astronomers discover Uranus and then eventually conclude that Neptune had to be out there based on their theories. And then eventually they did discover Neptune. So we'll learn about that today. During the Copernican revolution, the Danish astronomer Tycho Brahe was collecting a lot of data on the positions of the sun, moon, and the planets, but this was before the telescope. But these positions were recorded with a great amount of accuracy. And then the data that he collected would eventually be used by Johannes Kepler to derive the Kepler's laws of planetary motion. This was incredibly important because now astronomy has a mathematical framework from which we can make predictions and understand how these objects and bodies will move in the sky, and then be able to make predictions on where they will be in the future with great accuracy. However, Brahe wasn't a mathematician in himself, so he wasn't able to actually analyze the data or actually do really anything with it except record it and be like, haha, I have recorded a bunch of data. I don't know what it means, but it is mine. But eventually, when he left Denmark, he met a young mathematician by the name of Johannes Kepler who would figure out what to do with all that data. So despite having all of this lovely data but not being able to analyze it, Brahe was very vain and selfish and didn't want Kepler to analyze it. Brahe feared that if Kepler was able to gain access to his data, then Kepler would discover a new theory of motion, and this would rob Brahe of any glory and keep him from getting a place in history. However, after Brahe died, his data was released and Kepler was able to analyze it, and he released in 1609 his three laws of planetary motion. So now let's discuss Kepler's laws that he derived from Brahe's data. The first one is that the planets orbit the sun in an elliptical orbit, with the sun at just one of the focal points of the ellipse. Originally, early astronomers and philosophers thought that the planets would move in circles because it seemed most elegant. However, using scientific data, Kepler was able to show that all of the planets move in ellipses. His second law is a little complicated, so it's really useful to look over at the GIF we have in the lower left, because this kind of gives a visual representation of what I'm about to say. So for Kepler's second law, if you create a straight line between the planet and the sun, and as the planet moves around in its orbit, in the elliptical orbit, as that line sweeps out an area, that area is equal in space for any equal time interval. So I know this sounds weird, but what it really means is that as the planet is farther away and seemingly moving slower in its orbit, it's still sweeping out the same area as when it's closer to the sun and moving faster in the same amount of time. So the planet changes its orbital speed based on how close it is to the sun in its elliptical orbit. That's one way to think about this law. His third law is very mathematical, and it is that the square of the planet's orbital period is directly proportional to the cube of the semi-major axis of the orbit. Now, what this means is that the time it takes for it to orbit is proportional to the size of this orbit. And there are some constants of proportionality that we will learn about later. So I want you to recall from lecture 1 that scientific laws describe the principles through which theories act. Kepler's laws describe what a scientific theory of planetary motion in a heliocentric model would look like. They're not actually the theory that Brahe thought that they would be, and that theory wouldn't be developed for quite a bit longer. Kepler's first law states that planets move around the sun in an orbit which is shaped like an ellipse, with the sun at one focal point of the ellipse. So this seems relatively straightforward today that the planets would orbit not in perfect circles, but back in the 1600s, this idea was really controversial because it just seemed more elegant that planets would move in circular paths. So the paths that stellar objects traverse is what we call an orbit. And when Kepler looked at Brahe's data, mostly that of Mars, he was able to find that Mars was actually moving in an elliptical orbit instead of a circular one. And Kepler found that unlike a circle, which has a constant radius, the constant of an ellipse is the sum of the distance from the two foci inside the ellipse to any point on the ellipse. Now, what's funny is I actually learned more about the geometry of ellipses in my astronomy courses than I did in my math courses. So we'll go through a little bit about the geometry of ellipses right now. So the major axis is the length of the axis of the ellipse with the largest diameter. And the minor axis is the one with the smallest diameter. Now for a circle, the major and minor axes are the same length. But for ellipses, you are going to have ones that are smaller and larger than each other. Half of a major or half of a minor is called a semi-major or semi-minor axis. And through each semi-major axis are the foci. And we heard from the last slide that the sum of the two distances from each foci to any point on the ellipse is constant. Now you can categorize ellipses based on how round they are. So we define the ratio of the distance between the two foci with respect to the major axis as the eccentricity. Using this definition, you can think of a circle as an ellipse with zero eccentricity. This is kind of like how a square is a rectangle, but not all rectangles are squares. So a circle is an ellipse, but not all ellipses are circles. A circle is just an ellipse with zero eccentricity. So ellipses can become elongated from that perfect circular shape until it is completely flat, which then has an eccentricity of 1. So, for instance, Kepler found that Mars's eccentricity was really close to that of a circle, and its eccentricity was actually 0.1. So this is almost indistinguishable from a circle, but it actually is significant to planetary dynamics and motion. So Kepler's second law is a little complicated, but it's easier to think about it from the way he did when he was first deriving it. So he observed that planets, when they are in their orbit closer to the sun, they move faster. And when they are further away from the sun in their orbit, they move slower. So if we imagine a line connecting the sun to the planet, As that planet orbits around in a certain time interval, it sweeps out an area. And so these areas are equal for equal time intervals. So in this diagram, we see that when the planet is moving from 1 to 2, it sweeps out an area B. And then we see when it's further away in its orbit, moving from 3 to 4, it sweeps out an area A. And those areas A and B are equal as long as that time interval for both is equal as well. So now we've reached Kepler's third law, which states that the square of a planet's orbital period is directly proportional to the cube of its semi-major axis. So we know what the semi-major axis is. That's just half of the major axis of an ellipse. And we know what an orbital period is. That's just how long it takes for a planet to complete one revolution around the sun. So Kepler wanted to find a mathematical relationship between how these planets move in their elliptical orbits and how long it takes them to complete one orbital period. And he found through analyzing Brahe's data that there was a direct relationship between them. That the further a planet is from the sun, the longer it takes for it to complete a revolution about the sun. And we can think of this mathematically as the period squared is equal to the semi-major axis in astronomical units cubed. But we'll eventually learn that this is not the whole story. So despite all of these great advancements by Kepler, it wasn't until 1687 that when Isaac Newton published his Philosophia Naturalis Principia Mathematica, that we got an actual conceptual framework behind gravity. And we actually got some laws that described gravity and not just laws that described planetary motion. So Newton was a bit of an oddball and a recluse, and he would stay by himself in exile, a self-imposed exile, in his house and just work on studying the natural world. He was encouraged by Edmund Halley, that Halley's comet is named after, to publish his works into 3 books, which became known as the Principia, and they are considered one of the most important works ever in the history of science. So now we have reached Newton's laws of motion, which some of you may have encountered before in a physics or science course. These laws govern all motions and the dynamics of all objects, and they set the stage for his first book, Of the Motion of Bodies. So Law 1, how he stated it, was that every body preserved in its state of rest or uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon. So put more simply, an object will remain in either rest or motion at a constant speed unless acted upon by an outside force. Law 2 says that the alteration of motion is ever proportional to the motive force impressed, and it is made in the direction of the right line in which that force is impressed. Or more simply, force is equal to mass times acceleration. This is F equals ma. This is that one of those fundamental physics equations that you first encounter in a science or physics course. And then law 3 states that every action there is always opposed and equal reaction, or the mutual actions of two bodies thereupon upon each other are always equal and directed to contrary parts. Or put more simply, for every action there is an equal and opposite reaction. So now let's talk about Newton's first law. This was originally called Galileo's law of inertia. And this is the one that states that an object at rest or an object in motion at a constant speed will stay at rest or at that constant speed unless acted upon by an outside force. So in physics, we have this term called momentum, which describes how an object is moving and that momentum only depends on the object's mass and its velocity. So momentum is equal to mass times velocity. So applying this definition of momentum to Newton's first law, it simply states that no matter how much time passes, an object's momentum will be the same at any moment unless it is acted upon by an outside force. Newton's second law of motion was based on the works of Galileo. Galileo was fascinated with this idea in the changing of motion, that is, an object's acceleration. So, law 2 states that the change of motion is proportional in the direction of the force acting on it. So, a force, as Isaac Newton described it, is the action on or of a body. We can think of this as a push or a pull on something. And Newton found that the force acting on a body is proportional to the change in that body's motion. So if you push something forward, it moves forward. You pull it back, it moves back. If you apply more force, you push harder, it moves faster. And if you apply a little less, it moves slower. So we can think of a change in velocity with respect to time as acceleration. And so if we then want to think of this law mathematically, we can say that a force is equal to the mass of the object times its change in velocity with respect to time. That is its acceleration. So we can now say F equals ma, and we understand what that means. So now we've reached Newton's third and final law of motion, and this is the one that states that for every action, there is an equal and opposite reaction. So if you are pushing on the wall and applying some force to that wall, that means that the wall is also pushing back on you and applying an equal and opposite force to you. Opposite meaning that it is in the opposite direction. But when we apply Newton's third law with his first law, this implies that all of the forces in the universe don't just exist by themselves, but exist as the result of other things acting upon them. So now let's think about Newton's apple, his famous apple that gave him this burst of insight into how the universe works. The apple fell on his head because of gravity. It changed its velocity as it fell, it accelerated, and then something had to act on the apple to get it to accelerate. When Newton thought about his laws of motion and what consequences came from them, he discovered that he really needed to create a new mathematical framework to understand his observations. The force of gravity acting on that apple wasn't just on that apple. Gravity acts on all objects, not just here on Earth. And so to really understand what was happening, he developed calculus because he wanted to understand these observations and he wanted them to remain consistent with the current laws of planetary motion. So the universal law of gravitation is that there is a gravitational force between all bodies with mass. This is very, very profound. That means that technically you are pulling on the moon and the moon is pulling on you. Newton concluded that the force, this attractive force of gravity, is proportional to the inverse of their distance squared. This is a citing of that inverse square law. This F equals ma is one of the most famous equations in history. It's very profound, it's very useful, and it changed the way that we think about the world. So now we can look at the equation for the force of gravitational attraction. And this is from that equation F equals ma. So the force of gravity is equal to the universal gravitational constant times the mass of the two objects that we're looking at the force of gravity between. And then that's divided by the distance between the two squared. To confirm this law took generations of scientists and just incredible amounts of data and lots of experimentation. But rigorous testing of this proved that this was indeed true. We now have evidence from Newton's laws to support his theory of gravity. In fact, you can use Newton's second law and Eratosthenes' calculation of the Earth's radius, and you can calculate the force of gravity on the Earth and the acceleration of gravity on the Earth. So now let's connect Kepler's third law with Newton's laws of gravity. So Kepler's third law stated that the orbital period was proportional to the semi-major axis cubed. But we also know that in the astronomical units that the period squared was equal to the semi-major axis cubed. So Newton was able to mathematically confirm Kepler's third law, and he actually found that that the proportionality that made these equations work was that you needed to have the sum of the two masses times the period squared, and then you could get the semi-major axis cubed. Now, these may seem different, but these are actually the same. And that's because we were originally talking about Kepler's third law in terms of astronomical units. So this is where the choice of units becomes really important. So Newton was able to discern that the constant of proportionality, this m1 plus m2, is equal to 1 in astronomical units because we can think of the sun's mass as being so large and so much greater than the planet's mass that it's pretty much the dominant term. And this is a huge moment in scientific history because this shows that when the units used can really affect the result itself. How we measure things is very important in how we do science. Now, armed with Kepler's laws and Newton's laws of gravity, let's look at these orbits of the planets in our solar system. This is a pretty complex problem because now we know that the mass of every object attracts the mass of every other object. So we can't just think of the solar system as the Earth orbiting around the sun, but as all of the planets orbiting around the sun and all of the planets having these gravitational interactions with each other as well. This is a very complex problem, and it was readily apparent to astronomers and mathematicians at the time that this was a very complex problem indeed. And so this is why they had to develop such tools as calculus. So Kepler's first law stated that there were two distinct points in the orbit of a planet where it was closest to the foci, the perihelion, and when it was furthest from the foci, the aphelion. But if we include Newton's universal laws of gravitation and motion, then if all the celestial bodies, even our moon, follow an ellipse, then there must also be two distinct points in their orbits, the perigee and apogee, where they have distinct values of gravitational force and values of speed. When we look at the solar system and the orbits of all the bodies in it, we have seen that they are all ellipses of various degrees of eccentricity. And it turns out that most of the planets in our solar system have very low eccentricity, ranging from 0.01 all the way up to 0.09. Turns out, though, that Mercury greatly exceeds this and has an eccentricity of 0.21. So Mars has a relatively large eccentricity compared to some of the less eccentric orbits in our solar system, But this was still enough to determine that Mars's orbit was elliptical. And all of these planets orbit together on a common plane. This is known as the orbital plane. We can think of this as if you put all of the planets on a table and had them roll around the sun at the center, they would all be able to do that on the plane of the table without a whole lot of dipping up and down through the table itself. Just like the planets in our solar system, many of the other natural satellites have eccentric orbits. When I say natural satellites, I mean like asteroids and comets. Most asteroids have pretty small semi-major axes than the other natural satellites and can be found primarily within the asteroid belt between Mars and Jupiter. Comets, on the other hand, have very large semi-major axes and huge eccentricities, zero point 0.8 or higher. And so this means that comets spend most of their lifetime far away from the sun, which means that according to Kepler's second law, they're moving very slowly. But as the comet gets closer to the sun, it moves faster. And also, as it gets closer to the sun, it gets a little bit warmer. And so, comets, being balls of ice and dust, start to melt as they get closer to the sun. And that melting gives it that very long, beautiful tail that we associate with comets. And so, we see that as comets move in to the inner part of the solar system in their orbits. On the last slide, you may have noticed that I said natural satellites to describe asteroids and comets. That implied that there are non-natural satellites, these artificial ones. And you knew that because humans have been launching satellites into Earth orbit and actually into orbits in the solar system for quite a while now. We call these man-made satellites artificial satellites, and they are often placed in orbits around Earth that require them to be ejected from the Earth's surface. They have to have a certain speed to escape the gravitational pull of Earth. They have to have an escape velocity. And for Earth, that escape velocity is roughly 11 kilometers per second. So if you could throw a baseball at 11 kilometers per second straight up, it would actually leave the Earth's surface and reach a stable orbit around the Earth very far away. Unfortunately, I don't think any of you can throw an 11 kilometer per second baseball, because if you could, you wouldn't be in this course, you'd be in the MLB winning all the awards. Applying Newton's laws of gravity actually helped in the discovery of the planet Neptune through the discovery of the planet Uranus. So, Newton's universal law of gravity states that every body with mass experiences a gravitational attraction to every other body with mass. This means that the planets in our solar system, while they orbit around the sun, occasionally tug and pull on each other and make their own orbits a little wonky. So, the amateur astronomer William Herschel accidentally discovered the planet Uranus in 1781. He used his telescope to discover that it was indeed a planet. And after a couple decades, or not a couple decades, a little bit less than a decade of calculations based on measurements of Uranus's position in the sky, its orbit could be calculated. However, there were some weird parts of its orbit. There were some weird aspects of its orbit. Astronomers saw that occasionally Uranus experienced little disturbances in its orbit, and this was not in line with our understanding of planetary motion. So, In the 1840s, a man by the name of John Adams, not one of the founding fathers, just another man by the name of John Adams, presented an analysis of Uranus's irregularities in its orbit, and he hypothesized that there should be another planet that is more distant than it that is causing it to have these wobbles in its orbit, that the pull of another further planet was likely causing these motions. At the same time, Urbain Joseph Le Verrier, I don't know if I pronounced that right, hypothesized and published his own results on this mystery planet. But he was not able to find it, so he enlisted a colleague, Johann Gall, to look for the planet, and that very night they found the planet in the spot that had been predicted by George Airy. This discovery of Neptune was a huge triumph for gravitational theory and all of the scientific groundwork that had been laid out by Galileo and Kepler and Newton. And I'll even include Brahe for recording that data because Kepler needed that data to make his leaps. This was Neptune's discovery was one of the first times in scientific history that predictive scientific laws actually led to the discovery of something new. John Adams, the mathematician, not the founding father, and the French astronomer Le Verrier were honored for this discovery. And their well hypothesized belief that this planet must exist due to the irregularities in the orbit of Uranus. This discovery really certified that the approach of the scientific method was valid and could make grand discoveries, and this laid the foundation for many new discoveries in our universe, many of which we'll learn about in this course. This concludes Lecture 3.